Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl from lunchboxsessions.com. In this video, we will determine the sources of flow that are found on the K-strain line from a pressure-compensated pump. Most pressure-compensated pumps have, at minimum, 3 main hoses connected. There's an intake line coming from the tank to feed fluid to the pump. There will be an outlet or an output port sending out flow to the hydraulic system where we have valves and cylinders. And then there will be a third hose, sometimes the smallest of the 3, and this hose, referred to as the K-strain line, usually leaves from the top of the pump's case and goes back to tank. We have the tank reservoir symbol showing here. The reason why it's important to understand the sources of the flow on the K-strain line is to help understand the importance of maintaining a clear line back to tank with no obstructions present for the sake of the life of the pump. It's also important to understand the K-strain flow as it relates to volumetric efficiency, a topic we cover in other videos. And some pumps, such as flow compensating or load sensing pumps, make very small corrections to the swash plate position, or said another way, to the displacement of the pump, to compensate for minor changes in the loading of the hydraulic system. And knowing something about the K-strain flow helps understand those pumps and how they function as well. So, where is the flow coming from that we see on the K-strain line? So just going back to some of the basics for a pressure compensated pump for a moment, remember that we've got a cylinder barrel with a number of pistons that are always rotating if the prime mover is functioning. You'll see over on the left a 3-dimensional mimic to remind us that those pistons in the cylinder barrel, there's usually 9 of them. Some pumps have 7. Those pistons in the cylinder barrel are constantly rotating around the shaft, and we're just looking at a 2-dimensional cutaway of a frozen moment in time for the shaft's rotation. So I've got the pressure compensator set to 1500 psi, and remember that in this basic system, we will develop system pressure just using a basic restriction on the pump's outlet, the needle valve over here on the right. So we'll build up system pressure by simply closing down on the needle valve, and you'll see the pressure building up. And of course, there will come a point where all of a sudden we'll see that the pump has entered the active region. We won't go into details about what the active region is on this particular video. Suffice it to say that the pump has begun to compensate for the fact that we're coming close to the maximum system pressure. Our maximum system pressure was set at 1500 psi, and here we are above 1400. We're very close to the top pressure. And so, a pump that has the ability to be variable displacement is now showing that it has changed the angle of the swash plate. If you were observing at the beginning of the video, you saw that we had 10 gallons per minute of flow present, and now we are below 7. So our pump is in the active region, and where that gets interesting is that our flow arrows on the K-strain line have gotten larger to prompt us into noticing that the flow rate on the K-strain line has increased. Now, it would be a mistake to think that all of the flow that has gone missing on the outlet port, roughly 3.3 gallons per minute in this example, is now present on the K-strain line. Now, that's not true. It is a common misnomer for some who are not yet familiar with the inside of a piston pump to think that a piston pump is merely a type of pump that has its relief valve on the inside of the pump. I've heard that said before, and that's not at all the case. A pressure compensated piston pump does have a way of limiting maximum system pressure, which is a function similar to a relief valve, but it's handled in a different way. But no, in this case, the flow has increased on the K-strain line for a few reasons that we'll have a look at now. If you're familiar with the principle of a fixed orifice in a hydraulic system, anytime you increase the pressure on the inlet side of that orifice, the flow rate through that orifice will increase. So inside of a piston pump with all of the moving pieces, there are clearances, for instance, between the piston and the cylinder in the cylinder barrel. And remember, there's 7 or 9 of those, so there's clearances there. There's typically a bit of clearance on the back of the slipper pads, or piston shoes as they're sometimes called. Those shoes are floating on the swash plate. There is also the piston ball, which is crimped into place on the piston shoe. There's a minor amount of clearance there. And all of the cylinder barrel on its porting face is rotating against a porting plate inside the piston pump as well. So there's a rotating piece and a stationary piece. And that porting plate is a minor clearance as well. So many clearances, all of them I said they were minor clearances, but if we add them all together, they make up a fairly substantial cross-section of orifice opening inside the pump. So anytime when the pressure increases inside the pump, as is happening for all of the pistons that are working against the outlet as they eject oil from the pump into the hydraulic system, all of those pistons are under fairly high pressure, the cylinder barrel as well. And so you're seeing little white arrows in a number of places in our animation. And then also consider the pressure compensator, sometimes referred to generically as the controller on the pump. In most cases, the controller on the pump requires a flow of fluid in order to carry out its basic functions. And indeed, you could see flow is taking place. Well, when the pump is in the mode where it is pressure compensating, outlet fluid is being pushed into the control piston. But when the pump is coming back on stroke, oil that was in the control piston has to be ejected. So quite often when you read a piston pump manufacturer's notes about their design, they will refer to controller exhaust that will be present on the K-strain line. They're simply talking about fluid that was used to move the swash plate or some other control function in the pump and now needs to be removed from the pump in order to allow the controller to go back in the opposite direction. So controller exhaust in this case is simply oil leaving the pressure compensator as the pump goes back on stroke. All of those clearances, and in some languages when you read the notes for a piston pump, they literally refer to this fluid in a word that translates to leakage oil. We're not necessarily talking about bad leakage, but it is internal leakage between components that have a clearance. That fluid together with controller exhaust comes together, and all of that is present on the K-strain line. Manufacturers recommend a maximum amount of back pressure present on this line, meaning let's not see this line get too narrow in diameter. It's important not to have a filter that could cause blockage on the K-strain line. Always a little controversial to put a filter on the K-strain line. Mixed reviews about how that works out. Depends on the pump manufacturer and how carefully the user of the pump maintains that. As you can imagine, partial blockage on the K-strain line will restrict the flow of K-strain fluid leaving the pump, and complete blockage of the line, of course, would cause all of the lubricating flows that are occurring inside the pump. We're lubricating the back of the slipper pad against the swash plate. We're lubricating the piston ball as it is socketed into that slipper pad or piston shoe. We are lubricating as well the cylinder barrel against the porting plate. Obstruction on the K-strain line could reduce or stop all of those flows, and the pump could very quickly move to catastrophic failure without that critical lubrication. In addition, blocked K-strain line will cause our pressure compensator function to misbehave or cease entirely. The malfunction may be no pressure compensate function is available. So again, the pump could easily move to a catastrophic state without maintaining K-strain flow. But all of this K-strain flow occurring, of course, is a loss of fluid at the high pressure that otherwise could have been available to us on the outlet and sent to hydraulic valves and cylinders. So we've paid the price of volumetric efficiency. At high pressures, a certain percentage of our flow is on the K-strain line, especially once the pump is in the pressure compensate mode. Here, let me just restrict that needle valve to the maximum. The pump has gone off stroke. It's still testing to see if there is a flow path present. And of course, our needle valve is closed. The only flow path present is the internal leakage of clearances inside the pump. So the pump only goes back on stroke a very small amount of degrees. And at this moment, our K-strain line will be at the maximum possible flow. And for a very high quality pump at very high pressures, that might be in the range of 5%. For some very large pumps, it could be up to 10%. And for some very small or very poorly manufactured piston pumps, that flow rate could be 15% or more. 15%, that is, of the pump's maximum output displacement for its regular flow. So it's not uncommon to see 10% of the maximum displacement of the pump present on the K-strain line when we're at maximum pressure. One additional source we should point out here just before we close off is that in order to keep the control piston from driving the swash plate right over center would be a very damaging circumstance. To limit the travel of the swash plate once we reach the 0 point, quite often a bleed orifice is present on a tube where the control piston is sliding back and forth. So that's another clearance inside the pump where K-strain flow originates from. So once again, the slipper pad against the swash plate, the piston ball as it is socketed into that slipper pad, that's a critical point to lubricate and a clearance. The valve plate or porting plate at the back of the pump, the cylinder barrel meets the porting plate, and controller exhaust, and then maximum stroke for the control piston, a bleed orifice for that. So that's a bit of an introduction as to where K-strain flow originates from inside the pump. Thanks for watching.
We have hundreds of interactive resources like this live schematic, so you can try out your wild ideas without blowing anything up. Get started at lunchboxsessions.com.